All right, continuing chapter 9, we are going to look at another reaction type, and that is shown on this slide. So notice that the starting material here is a tertiary alkyl halide. And that it is reacting with water to make the alcohol. But we know that tertiary alkyl halides do not react through an SN2 mechanism. The tertiary alkyl halide is a poor electrophile and water is a poor nucleophile. So how does this reaction actually make the final product? Because we know that it does. And it's actually surprisingly fast. So if it can occur by an SN2 mechanism, then it must be occurring by a different mechanism. And that mechanism is called SN1. The rate of this mechanism depends only on the concentration of the alkyl halide. So again, the number 1 for the name refers to number of reactants the rate depends on. So SN2, the reaction depends on 2 reactants. The rate depends on 2 reactants for an SN2 reaction. That is the alkyl halide and the nucleophile. But for an SN1 reaction, the number of reactants the rate depends on is 1, and the only reactant that can affect the reaction is the alkyl halide. The nucleophile, changing the concentration of the nucleophile has no effect on the rate. And so essentially you can think of it in this way. Recall the zero order reaction or the zero order substance. So if alkyl halide is first order, and so it is raised to the power of 1. And then the nucleophile is zero order. So it is raised to the power of 0. But remember that raising a substance to the power of 0 makes that substance equal to 1, the number 1. And so the nucleophile does not factor into the rate of an SN1 reaction. This type of substitution is called substitution nucleophilic unimolecular, so that the rate depends only on 1 molecule, the alkyl halide. This reaction is going to occur in the following way. We're going to have our alkyl halide, and in the first step of the reaction, which will be the rate determining step, the halide will simply fall off, taking the bonding electrons with it to create a carbocation. The carbocation will then be attacked by the nucleophile, which may be either weak or strong, and the nucleophile will bond to the cation, giving the final product with the nucleophile in place of the halogen. Now, because this goes through a carbocation intermediate, inversion is not the answer to the final product. We're going to have a racemic mixture of products for any SN1 reaction that produces a molecule with a chiral center. Whoa, what did I? Okay, let's see what notes I have. So it always occurs through a carbocation intermediate. Here we go. This SN1 reactions often occur by solvolysis, and in a solvolysis reaction, the solvent used to dissolve the starting material is often also the nucleophile of the reaction. And that's called solvolysis. The solvent is the nucleophile. Okay, so we have and SN1 reactions favor tertiary products because the most stable carbocation of an sp3 carbon is a tertiary carbon. So the way that this is going to occur is that, oh, yeah, I'm just checking to see if I already had it. The halogen falls off in the first step, and then the alcohol bonds at the positive carbon. So note that this structure here is the skeletal structure of the alkyl with 4 carbons and a methyl branch. 1, 2, 3, 4, and our methyl branch. So the nucleophile, our solvent, is going to come and bond at the positive charge. That will produce this protonated alcohol product, or protonated ether product, so that the alcohol oxygen is bonded now at the carbon that was positive, but it still contains, that oxygen still has bonds to hydrogen and the methyl group. In the final part of the reaction, we made an ether. We must deprotonate the oxygen to get to the ether position. The solvent will also remove the proton so that we form this protonated alcohol product by using the alcohol to remove the hydrogen from the ether oxygen to give us our final product, this ether. Okay, so as I said, first the halogen falls off. This is the slow step. This is the rate determining step, or RDS, rate determining step. So that's going to be the absolute maximum on an energy graph. In this case, we're using water as the nucleophile, so water is bonding at the positive carbon. This makes a protonated alcohol. Another molecule of water will come and deprotonate to give the final alcohol product and an acid. In the mechanism for SN1 reactions, the first step is always departure of the alkyl, of the halide atom to give the carbocation. So we go from Rx to R carbocation. Here's our intermediate cation. This is the rate determining step, so it's the absolute maximum on the graph. At this point, we have both our halide and water present. Water acts as the nucleophile, giving our second intermediate, our protonated alcohol, and deprotonation gives the final product, the alcohol. So for substitution reactions, in general, primary alkyl halides undergo only SN2 reactions. Secondary alkyl halides undergo SN2 reactions most of the time, and tertiary alkyl halides undergo SN1 reactions. There will be circumstances where secondary alkyl halides undergo SN1 reactions, but they will be special circumstances. Okay, so when we have The example we have here is a tertiary alkyl halide reacting with water. Note that the product of this reaction, because the three different R groups are different, R, R prime, and R double prime, because they're not the same thing, we get two products that are enantiomers. If the leaving group in an SN1 reaction is attached to an asymmetric carbon, then the products will be a racemic mixture, a pair of enantiomers. And that is because the intermediate is the pretend that this is trigonal planar geometry here, and imagine that all of these carbon bonds are planar. Then perpendicular to the planar bonds is this p orbital for the carbocation that forms as our intermediate. The nucleophile, water in this case, our nucleophile can bond either to the top of the p orbital or at the bottom of the p orbital. And how it bonds to the p orbital, when it bonds to the top, it gives us one set of, it may give us R or S, and when it bonds to the bottom. So if for example, bonding to the top gave R enantiomer, then bonding to the bottom would give S enantiomer, and that is how we would get our two isomers for our enantiomeric pair. So here's a depiction of that. We have our an alcohol here. Protein alcohol. Okay, so we have the alkyl halide and the halogen falls off. We then have this planar sp2 hybridized carbocation. Water combined to either side of the carbon. If it bonds at side A, we get this enantiomer. And not knowing the priority of the wedge versus the hatched versus the solid line, we can't say whether that's R or S, but it's one of the two enantiomers. If it bonds at the side B, we get the mirror image isomer, which gives us the enantiomeric pair. So these are our enantiomeric pairs. Most SN1 reactions lead to only partial racemization. We generally, while we almost always refer to SN1 as giving us a racemic mixture, the strict definition of a racemic mixture is a 50-50 concentration of an enantiomeric pair. However, that is not what the true concentration of the final products in an SN1 reaction. If the halogen is bonded to a chiral carbon before it leaves, the isomer that forms by water bonding to the side of the carbon that the halogen leaves from will be present in lower concentration than the isomer that forms from water bonding to the side of the carbon where the halogen is not present. So this is our example. If Br has diffused away, then yes, we could have a 50-50 mixture, but that's not actually true. We know that diffusion does not occur that quickly, and so if water bonds at the side opposite of where the halogen is leaving from, it's going to be able to form that bond or to collide with the carbon from the side that is not on the same side as bromine more frequently than the water can collide with the carbon when bromide is in the way. So when Br has not diffused away, it blocks the approach of water on the side of the carbocation from which bromine departed. And so in general, there's slightly more inverted product because the front side or the side with bromine is partially blocked. The side with the halide is partially blocked. Let's say instead of front side, the halide side is partially blocked. So we have experimental evidence demonstrating the SN1 reaction that helps us to accept the theory of its mechanism. Remember, all mechanisms are theories, and while we have evidence, we can never fully prove a theory. So the rate of let's look at the evidence for the SN1 mechanism. The rate of the reaction depends only on the concentration of the alkyl halide. So changing the concentration of solvent, changing the concentration of the nucleophile has no effect on reaction rate. But changing the concentration of the alkyl halide, if I double the alkyl halide, I double the rate of reaction. And so that is so the reaction does depend on the alkyl halide. Number 2, tertiary alkyl halides, but not primary or secondary alkyl halides, tend to undergo SN1 reactions. And so because tertiary alkyl halides favor SN1 reactions, that is evidence for the mechanism of going through the carbocation. Also, if the halogen is attached to an asymmetric carbon center, unlike SN2, where we get one enantiomer, in this case, we get a pair of enantiomers. So in an SN2 reaction, we have an asymmetric center as a reactant, then in the product, we get the inverted asymmetric center. And so only one set of a pair of enantiomers is present. But for SN1 mechanism, we get a pair of enantiomers, which is indicating that when the nucleophile bonds, it is bonding to an sp2 hybridized carbon. The weakest base is the best leaving group for an SN1 reaction. So this is still true. Okay, this is the same rules as occurred for SN2 are still true for SN1 in terms of the leaving group. The weakest base is going to be the best leaving group. And what they mean for the weakest base is iodide. So when it's dissociated from the R, it is a base. Iodide is a better, is a weaker base than bromide, which is a weaker base than chloride, and is a weaker base than fluoride. So if we're going for basicity, the strongest base, I may be saying the weakest base is the best leaving group. Iodide is the weakest base because it has the strongest acid. And so the iodide is less basic than bromide, which is less basic than chloride, which is less basic than fluoride. We're going from a pKa of -12 to pKa of 3 for the conjugate acid. So this is acid strength on the bottom row. Hydroiodic acid is a stronger acid than hydrofluoric acid. And then in the middle we have base strength, strong acid, weak base. So iodide is the weakest base. So iodide is less basic than fluoride. Hydrofluoric acid is the weakest acid, and so it has the strongest base. And the way that that helps us with reactivity is that the weakest base is the best leaving group. It has the weakest bond to carbon. And you can also know that from our periodic trends that as we go down a group and the atoms get larger, the bonds get weaker and longer, and when they get longer, they become weaker. And so hydrogen iodide is the lowest halogen on the periodic table from the 4 that we're looking at, and so it will have the longest and weakest bond. Comparing SN2 and SN1 reactions, remembering our carbocations, tertiary allylic is better than secondary allylic is better than primary allylic, and that primary allylic is approximately equal to tertiary allylic, is going to be relevant when you go forward and practice these SN1 reactions. So SN2 and SN1 reactions. SN2 is a one-step mechanism dependent on 2 reactants. Remember that the 2 of the SN2 refers to the number of reactants that affect the rate. So it has a bimolecular rate determining step. Two molecules matter in the rate determining step. The rate decreases with increasing steric hindrance for an SN2 reaction. If we compare SN2 and SN1, SN2 is a one-step mechanism dependent on 2 reactants. And SN1 is a 2-step mechanism dependent on 1 reactant. So remember that the numbers for the SN2 and the SN1 refer to the number of reactants affecting the rate. SN2 has a bimolecular rate determining step. 2 molecules determine the rate. SN1 has a unimolecular rate determining step. 1 molecule determines the rate. Rate For SN2, the rate decreases as steric hindrance increases. And for SN1, the rate decreases with decreasing stability of the carbocation. And so as the substitution of the carbon gets less, SN1 rate decreases, but for SN2, when the substitution of the carbon increases, the rate decreases. So while SN2 covers our primary and secondary carbons, SN3 covers a completely different, more substituted carbon, the tertiary. In SN2, the product has an inverted configuration relative to the reactant, so that R goes to S or S goes to R as a result of the reaction. But for SN1, both products have both retained and inverted configurations. So we make both the R and the S configuration. For the leaving group, the stability of the leaving group is the same for both SN2 and SN1. The most weakly bonded iodide is the best leaving group, and the most strongly bonded fluorine is the worst leaving group. In terms of the substitution of the alkyl halide, SN2 reactions can occur with methyl primary and secondary substituted carbons, but SN1 can occur with tertiary and sometimes secondary. Okay, then the better the nucleophile, the faster the rate of reaction. And the strength of the nucleophile for the SN2, the better the nucleophile, the faster the rate of reaction. So we have to be able to rank our nucleophile in terms of its reactivity, and sometimes we even have to consider if the nucleophile, whether or not the nucleophile's reactivity is affected by the solvent. In the SN1 reaction, the strength of the nucleophile does not affect the rate of the reaction, and so the solvent effect on the nucleophile is irrelevant. Okay. Some reactions will have both, will be multiple step reactions, where in one part of the reaction there's an SN2 reaction occurring, and in another part of the mechanism a cation is seen, and so it's an SN1 reaction. If our overall mechanism contains both SN2 and SN1 reactions, then the rate will depend on both. Okay, primary alkyl halides and methyl halides. They cannot form carbocations, so they only occur in SN2. Secondary alkyl halides. Carbocation formation is usually too slow to make up for the large concentration of the nucleophile in a solvolysis reaction, but some of the product will be a result of carbocation formation. And so both SN2 and SN1 are occurring simultaneously, but SN2 occurs more quickly than SN1. For the tertiary alkyl halide, only SN1 is occurring. They cannot undergo backside attack. But if you remember at the beginning of the chapter, we said that in chapter 9, we were going to consider both substitution and elimination. And the thing is that reactions that can undergo substitution can almost always also undergo elimination. So alkyl halides undergo substitution and elimination. We've covered our substitution reactions, both SN1 and SN2, and next we're going to cover our elimination reactions. In an elimination reaction, a halogen is removed from one carbon and a hydrogen is removed from an adjacent carbon. So that a double bond is formed between the two carbons from which the atoms were removed. There are two types of elimination reactions. One depends on both reactants, the nucleophile and the alkyl halide. And the other type of elimination reactions depends only on the alkyl halide. So we call them E2 and E1, elimination bimolecular and elimination unimolecular. In the first type of elimination reaction, we have a one-step mechanism where both the base and the alkyl halide affect the rate of reaction. And so we have a generic base, B, with a lone pair that can remove a hydrogen atom. And that's the first step. At the same time that the hydrogen atom is being removed by B, the bonding electrons of hydrogen form a pi bond, and when the pi bond is formed, the halogen is kicked off. So the halogen gets kicked off, and we get our alkene final product in one step. For an E1 reaction, this is going to occur when we can form a stable carbocation. E1 is going to be possible. And it's also important to note that tertiary alkyl halides can undergo either E2 or E1 mechanism. So how can you distinguish whether this tertiary alkyl halide is going to undergo an E2 elimination or an E1 elimination is going to depend on the strength of the base and the type of base present. So we'll have to cover those topics as we move through this section. But generically, in an E1 elimination, we first form the carbocation by dissociation of the halogen. That gives us our tertiary carbocation shown here. In the second step, a base in solution will come in and remove a hydrogen atom, and the bonding electrons for hydrogen will form a pi bond, removing the positive charge by now giving the positively charged carbon an octet. And that's how we obtain our final alkene product through the carbocation mechanism. So we're going to start with an E2 reaction. But let's do that on the next video.